So as I was mentioning, the sample means pile up around the population mean. So basically, if you're taking means of the different samples, you would expect them to be around the mean of the population. The mean of the population is, the average score in that population. So considering that these samples are considered to be representative of the population, you would expect that. The distribution of sample means is approximately normal in shape. So the larger the sample size, the closer the sample means should be to the population mean. So this goes back to the idea that larger samples should be better representative of the population. So we're not talking about the number of resamplings, we're talking about the actual number of scores in the sample. And so as you increase the number of scores in each sample, that is going to be a better approximation of the population mean than if you have fewer scores in your individual samples. I'd like to go back to this point right here as well. So the distribution of sample means is approximately normal in shape. There's two considerations to this, and I'm going to go over them again in a minute, but I want to present them here. One is that the distribution of sample means is going to be normal if the original population from which the sample means are drawn is normal. If it's not normal, the distribution of sample means becomes approximately normal whenever our sample size, so whenever the number of scores in each sample increases to at least 30 or higher. So you have to increase the number of size, and then for each sample size, and then it's going to approximate normality. Okay, so what I was going to ask y'all to do is to use this population of n of 4 to construct a distribution of sample means for n equals 2. How many samples would there be? So I went ahead and did this in Excel so you guys can see. Let's see if I make it bigger. Okay, don't worry about this over here. We'll come back to that later. But so we have here excuse me, a population with n equals 4. Big N representing population, little n representing sample. We're using that to construct a distribution of sample means for n equals 2. So how many samples are there? Well, you can have 2 and 2, 2 and 4, 2 and 6, all the way down. There are 16 different samples that we can compute from that include a sample of 2 from a population of 4. So what I'm asking you to do here is to, what I would like you to do is to think about what this would look in terms of a sampling distribution. So if we go to the next slide, what we would do is take each of these samples of 2 and find their mean. Then we would plot them. Whenever you did that, it would look something like this. You can practice it. It's also from your book. If you look on page 173, this is there. And so whenever you plot them and put them on your frequency distribution of sample means, it looks like this. This looks really normal, right? We can also see that the vast majority of the sample means are around the population mean. So we had scores of 2, 4, 6, and 8. And so the population mean is 5. Well, that's what we're seeing here too, right? And so the goal is to really answer questions, to answer probability questions about sampling means. So we can use this right here and say, what is the probability of drawing or having a sample mean greater than 7? Well, if we look here, there's only one sampling mean that we calculated that was greater than 7. And we know that there were 16 possibilities. So it's 1 out of 16. We applied this exact same thought process to individual scores. If you were given something like this and you said, what is the probability of obtaining a score greater than 7? You would look at this, you can count these if you want, and then say, well, there's only one, so it'd be 1 out of 16. Same thing. What is the population of M of a sample mean greater than 7? 1 out of 16. Okay. So it's often impossible to obtain every possible random sample. Here, we were able to do that because we had such a small population. But in reality, it's just not possible. It's not something that is something we can actually do. Now, the central limit theorem has been developed and is used to specify the shape, the central tendency, and variability of the distribution of sample means. And so this is a very important theorem because it can take what limited information we have and help us to, extrapolate that to population parameters. And that's essentially what we're trying to do, right? So this theorem helps us to provide a more precise description of the distribution. That is to say, if you went through the process for every random sample. In all likelihood, you're not going to do that. You're not going to be able to do that. And so we use this theorem as a way to help move our science forward. The standard error of the mean, this is an indicator of variability. I mentioned standard error earlier on. We're going to go into it some more. I would encourage you to take some time, read your book, read the chapter. I think that it's going to be really difficult to solidify this information if you haven't taken the time to actually read about it. So as I was mentioning, the standard error of the mean is an indicator of variability, and it measures how well an individual sample mean represents the entire population. So, to a degree, this kind of sounds like standard deviation. We'll talk about that in a few minutes. Okay, so let's dive in and discuss the central limit theorem. So there are some key things to remember about the central limit theorem. The first is that it applies to any population with any mean and any standard deviation. The shape does not matter, the mean does not matter, the standard deviation does not matter. It applies to all populations. The distribution of sample means approaches a normal distribution as n approaches infinity. This goes back to what I mentioned earlier when we were discussing the sampling distribution and how the distribution of means approaches a normal distribution. It is approximately normally distributed. That information is really informed by the central limit theorem, which says that as n approaches infinity, the distribution of sample means approaches a normal distribution. At about 30, so sample size at about 30, so having 30 individual scores in each sample, the distribution of sample means is almost perfectly normal. So you only need about 30. Anything less than that, it's not going to be as normal. I think that there's some flexibility with that, but you know that this is where the idea of having larger sample size really comes into play, and I think that this highlights the importance of that. So distribution of sample means for samples of size n, so of a particular size that you have predetermined will have a mean of, it's called the expected value of the mean, okay? Again, the distribution of sample means for samples of size n will have a mean of the expected value of the mean. Okay? We'll go over that a little bit more. I think that, let me find it in your book. I would say look on page 176 because it gives some good information about this. So that is one consideration. Additionally, the distribution of sample means for samples of a particular size, so of size n, will have a standard deviation of standard deviation divided by the square root of n. This is also going to be standard error. This last part right here, this represents standard error. This is the standard deviation of sampling means, standard error. So as I mentioned, there are important considerations of a distribution, and the central limit theorem addresses all of them. It addresses shape, distribution of sample means approaches a normal distribution as n approaches infinity. It addresses central tendency, the mean. A distribution of sample means for samples of a particular size will have an expected value of the population mean, which I'll talk about again, and then variability. Distribution of sample means for samples of size n will have a standard deviation equal to standard deviation of the population divided by the square root of n. So the central limit theorem really addresses all of these key considerations of a distribution. And what it does is it does this in a sense of, or in the context of sampling means. Okay, so I think we're going to break down each of these and go into them a little bit more. I've touched on this before, but just to go over it again, the distribution of sample means is almost perfectly normal in either of two conditions. This is not an and, this is an or. So if you are given a question like true or false, for a distribution of sample means to be normal, the population from which the samples were selected has to be normal, and the number of scores in each sample is relatively large, at least 30, that would be false, because technically it could be this or it could be this. So basically the distribution of sample means is almost perfectly normal in either of two conditions. One, the population from which the samples are selected is a normal distribution. If it's a normal distribution, then the distribution of sample means is going to be almost perfectly normal. Or the number of scores in each sample is relatively large, at least 30. Now this is regardless of the original shape. Okay, so the expected value of the mean. This is no different than what we've been talking about thus far when we discuss means. So the mean of the distribution of sample means is the expected value of the mean, okay, and has a value equal to the mean of the population of scores. This is very important. So the mean of the distribution of sample means is the expected value of the mean and has a value equal to the mean of the population of scores, which is this symbol. What does this mean? This means that if we were to take a particular n from a population, randomly sample that n, and do that an infinite number of times, or not infinite number of times, but do that until we have exhausted the number of possible combinations to create an n of our predetermined size, we were to graph them in a frequency distribution, and then we were to calculate the mean of that frequency distribution, if we were to calculate the mean of the sample means when we have collected sample means from all of the possible combinations of a particular n, that will equal the mean of the population. Let's go back to our example a little bit earlier. When we have a population of 4 and we construct a distribution of sample means equal to 2, we get this. Because our population is 4, we can see what the population mean is. The population mean here is 5. You can calculate it, it's 5. If you go through and you calculate the population mean here, or excuse me, the expected value of the mean, so the mean of all the means, you will get 5. This means that, again, if you were to randomly sample all of the samples of a particular n from a population, that the expected mean of all of those randomly sampled samples would be equal to the population mean. And that's what we can see here in this very simple example. Okay, this is essentially the mean of means. So basically we have a distribution of sample means and we're looking at the mean of that. That's all we're doing here. The expected mean of the distribution of sample means is called the expected value of mean, of the sample mean, okay? It is an unbiased statistic. Why is that? Whenever we discussed unbiased statistics earlier on, we identified one key characteristic of unbiased statistics. That is that the expected value of the distribution, well, let me just say what it is. Okay. It is an unbiased statistic when, if you were to take all of the possible distributions or all of the possible samplings of a particular n, and you look at things like the mean, after you have exhausted all of the different combinations of a particular n, the estimate of the mean is now equal to the population mean. Essentially, it's unbiased because over time, if you continue to resample for the same n, the expected value of the mean will be equal to the population mean. So M is an unbiased statistic because the expected value of the distribution of sample means is the value of the population mean. So if we were to exhaust all of the samplings of a particular n, find their means, and then find the means of those, that would be equal to a population mean. So at the end of the day, just remember the expected value of the distribution of sample means, right here, is equal to the population mean. Standard error of the mean. So now what we're moving into is variability. We were just talking about tendency, a central tendency metric, and so we're going to discuss the standard error of the mean. Let me take this.